Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is another video about harmonic motion. We just finished talking about simple harmonic motion, and now we're delving into damped harmonic motion, which is much more realistic in many situations. So let's take a look at what this looks like. So I have a little demonstration here, and if you watch, I'm just having this oscillatory object, and as it oscillates, something happens as time goes on. You'll see that it becomes a little more realistic than our simple harmonic motion in that the oscillations get smaller and smaller. Here was where we had the last deepest lowest point. Notice it didn't reach that point on the next oscillation, and it gets further away from that point on the next oscillation, and so on and so forth. So this motion here seems to be not slowing down, but getting smaller and smaller, getting more and more what we call damped. And I should speed this up just because honestly it's not entertaining to watch it go slowly, but you can see that it's less and less of a wiggle as time goes on. So let's go ahead and rewind that and see how wide the wiggle was to begin with. And you can see again that that oscillation becomes less and less as time goes on. And this is again much more realistic than simple harmonic motion, which never damps down. So what does this look like graphically? Well, let me press play, and you can see there's our cosine curve, or our sinusoidal function, if you will. But it seems to be getting smaller and smaller again as time goes on. Well, how does that happen? This is actually a wonderful topic in that it showcases what happens when you multiply a sinusoidal function like the cosine by any other function. Let me pause it because it's going to go backwards. By any function as a coefficient. What I've done is I've multiplied the front end of the cosine by e to the negative 0.02. And when you do that, let me showcase e raised to the negative 0.02, t. You can see it creates a ceiling for the oscillations. And I could put the negative one on there, but there's no real point for that. So you can see that as time goes on, that defines a maximal value for the oscillations, which is really a very neat idea. And this becomes more realistic as far as oscillations go. By the way, if you make that number, that 0.02, if you make that number slightly larger, the dampening happens faster. So I'll scroll back here and I'll make this number, instead of a 0.02, I'll make it a 0.1. And therefore this, I'm going to make a 0.1 as well. And therefore this, I'm going to make a 0.1 as well. And if you see, press play, we have that oscillation. I like how it's hitting the top and showcasing that, but you can see it damps down very quickly, right? And if you don't believe me, it's actually oscillating around the x-axis. So let me turn on the x-axis. It's just oscillating around that as time goes on. And in fact, it will still bounce back and forth between the x-axis forever. It'll technically never actually stop oscillating. So there will always be a little bit of airspace there. But that's the idea behind damped harmonic motion. And notice our coefficient is an exponential function. So here's the true definition of damped harmonic motion. If the equation describing the displacement of an object is given by these functions, y equals k e to the negative ct. In our cases, what we just saw is we allowed c to be a 0.02 and then a 0.1, but e to the negative exponent basically as time goes on. Those would be, as long as you have exponential coefficients like that, where c is positive and yet it has a minus sign in front of it, that causes the dampening. And so that's called damped harmonic motion. The constant is called, the constant c that is called the damping constant. So that would be like the 0.02 or the 0.1 in our Desmos app there. And k is the initial amplitude. That's as loud as that will ever be. The period is still 2 pi over that omega. So there's no difference with that. So let's start with like a typical mechanical example. Suppose the initial amplitude, k, is 0.3. The damping constant is c equals 0.2. Didn't have the equal sign there. And the frequency is 20 hertz. Find a model or a function that models the damped harmonic motion. Well, I'm going to go ahead and choose sine, but you could use cosine as well, honestly. The initial amplitude is 0.3. Remember, the formula is k e to the negative ct, and then I'm choosing sine. So there we go. And they told us that k is 0.3. They tell us that c is 0.2. So really, this pretty much nails down the entire formula, except for we don't know what omega is. But remember, the period is 2 pi over omega, and the frequency is the reciprocal of that. So the frequency is equal to omega over 2 pi. And they told us the frequency is 20 hertz, or 20 cycles per second. So we're going to go ahead and let frequency be 20 and solve for omega. That just means we have 2 times 20, which is 40, times pi, so omega is 40 pi. And we just insert that into our formula and we're done. Really not very much to do here. It's very mechanical. They would often tell you what kind of sinusoidal function to use, whether it's the sine or the cosine. I just chose the sine in this case. However, they might come back and say, nope, we wanted the cosine, and I would just switch it out for a cosine. Not that big of a deal. All right, so that's the mechanical example. Oh, and they want us to graph this function. To graph this requires a little bit of artwork here. We know it's not shifted up because there's not a plus D here. And we know there's no phase shift because, again, there's not a plus C in there. However, we do know that it's going to be a damped harmonic motion. So let me go ahead and get my ruler out here, somewhere up here. Yep, there we go. And I'll draw in my T axis. There it is right there. And now I don't need the ruler anymore, so I'll just take that out. So there's my T axis. And what I'm going to do is draw in the function that's going to be our ceiling, the e to the negative 0.2 t function. That's what I want to have as our ceiling. Actually, I should have this back so I could draw in my vertical axis, and I'm just going to draw it in right here. And I don't think I'll need anything else with that. And in blue, I'll graph y is equal to 0.3 e to the negative 0.2 t. The reason why is that's going to give me the ceiling for my amplitudes, or for my function. At time 0, we have 0.3 e to the 0th, or just 0.3. So I'm just going to pretend as though that's a height of 0.3. So it's a decreasing exponential function that goes through a height of 0.3. And at time, let's say 1 or 2 or whatever you want, I'm going to actually do time of 10. At time of 10, so y at time 10, we have 0.3 e to the negative 2. Okay, so that's 10 times 0.2. And that is likely just going to be somewhat shorter. We're graphing this by hand, so this is not really very scientific, but whatever. So I tried to carefully sketch out a decreasing exponential function. It's decreasing slowly, so I don't really need to be crazy about it. And then now we're going to graph in the sine function. At time 0, sine is 0. Otherwise, let's just go ahead and graph it in here. So there's a half period of the sine. Notice I'm artificially dampening already. In fact, I should dampen it a little bit more. If you really want a true nice way of graphing this, you should reflect this blue curve about the x-axis to get a really nice graph here. Let me go ahead and just do that. I was close enough. And that way it really guides me. And so I will then say, again, I'm trying to get, let's see, evenly spaced intervals here. So the next one will be like this. Didn't mean to have that in there. Next one will go through here. Again, trying my best to do evenly spaced. So this is pretty much a graph of, probably be like that. That's pretty much a graph of it. And if you're asked to label each of these points, which you might be asked to label like these key points here, that you don't have to label all of them. You could just find the period. We already found the frequency. Well, we found omega. So the period is 2 pi over that omega. And so what is that, 1/20th? Okay. Oh, I guess I could have just taken the reciprocal of this. But anyway, so 1/20th is our period. And so the step is 1/4 of that. So 1/80th. And so I could do this. This is 1/80th of a second. This here is at 2/80ths of a second. I don't know if your instructor is that stringent to have you label all these, but if they are, there you go, right? I've labeled one full period of it. It's technically called a pseudo period because this is not really a periodic function, but because it's being damped, but good enough, right? So there we go. That's a good by hand sketch of a damped oscillating motion or damped harmonic motion. Here's our second and final example in this video. And this is kind of an interesting example. So a tuning fork is struck and it oscillates in damped harmonic motion. That means that it's going to eventually peter out, right? You have some type of motion like this, it'll eventually die off. And the amplitude of the motion is measured at some point. They actually don't tell us what time it's measured, but they get that 3 seconds later, that amplitude has dropped to 1/4 of the measured value. So we are then asked to find the damping constant C for this tuning fork. Now, first of all, I'm going to just assume, without loss of generality, that the function for this is y equals k e to the negative ct. That's the damping coefficient. And I'll just assume it's a cosine omega t. Doesn't actually matter. The main thing you need to know here is when you measure the amplitude, it's over a certain amount of time. So, you want to measure it. It takes you a brief few moments to measure it. And during that time, it's enough time to oscillate to where your cosine part, the part that causes the oscillation, will become maximum. In other words, that cosine will become a 1. So really, when you measure it, you're really only measuring this piece right here. We're not really concerned about the wavering of the cosine. We're just worried about what's the maximal amplitude. And so at some point at time t naught, the amplitude, which I'll just say amp, is, let's just say k e to the negative c t naught, right? It's whatever that amplitude is. But then 3 seconds later, it is 1/4 of this. Well, what does that mean? It means that k e to the negative c times t naught plus 3 seconds is 1/4 of the but the measured amplitude at time c naught. Well, you could divide both sides by k, so that's fine. And in fact, I'm going to multiply both sides by 4 as well. So you get 4e to the negative c times t naught plus 3 is equal to e to the negative c t naught. Well, you could also go ahead and distribute this negative c into this parenthesis. So you get that 4e negative c t naught minus 3c is equal to e to the negative c t naught. Great. But we also know that from laws of exponents that you could write the exponential on the left-hand side as e to the negative c t naught times e to the negative 3c. Don't believe me? Multiply those two bases together, you'd add their exponents. And I can divide both sides by e to the negative c t naught. And so you get this, 4e to the negative 3c is equal to 1. Well, now I'm going to redivide both sides by 4 because I didn't realize I was going to actually need that on the right-hand side. And I'll take the natural log of both sides. And now I will divide both sides by a negative 3 over a negative 3. And then we can grab a calculator to approximate what this value is. And I will just do that with my calculator off to the side. If I can find my natural logarithm button, which I can, natural log of 0.25 and that divided by 3 and throw a negative in front, that is approximately 0.46. I don't know what they ask us to round it to. They don't. So I'm just going to say it's a 0.46. So that's how you would do that problem. That style of problem is actually really, I think, a tough problem for most students to grasp. That's why I chose to do that problem, mainly because also most other damped harmonic motion problems are pretty trivial to figure out. So I thought I'd do one that's a little more challenging or interesting. All right, there's not much else I could say about damped harmonic motion. It's a great application, but that's about it.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.